Very good evening, students. Welcome to the live session of Heat and Thermodynamics. Okay, in this session, we are going to cover the problems in the heat transfer and also the problems in the thermodynamics also. One of the very important chapters and very good questions are coming in the JEE advanced, okay, in the recent years and even in the past also. So lot of questions you will be having in these two particular topics. Okay, so without wasting much of the time, here we go. So first we'll see the problems in the heat transfer, some related problems and the related concepts in the heat transfer, and followed by the problems we are going to see in the thermodynamics also, and some of the easiest ways how we can make it in the thermodynamics. Okay, right. So here we go. So first, looking at the main some of the important formulas in the heat transfer. Okay, so you will be getting the questions mostly on the heat conduction also, and you will also be getting the questions on the Newton's law of cooling also. So mainly in the Newton's law of cooling, so one of the very important expression what we are going to see in the Newton's law of cooling, that is the rate of cooling minus of dt by dt, this is the rate of cooling is equal to n times T minus T naught. Actually, it is directly proportional to the temperature difference at that particular instant. So at any instant, whatever the rate of cooling you are taking, that is directly proportional to the temperature difference at that particular instant, and n we are calling it as Newton's cooling constant. So one of the most important concept here in the heat transfer is this one. And when you talk about the heat conduction, in the heat conduction, all that we are going to see is the rate at which heat is transferred, right? So that rate at which heat is transferred, dq by dt, any particular instant, the rate at which heat is transferred is always equal to minus Ka dt by dx. And let me tell you, in this heat transfer, and especially when you talk about in heat conduction, we are actually going to see the one-dimensional heat conduction equation. Okay, so it's only in the one dimension, either it is in the x direction completely, sometimes, or it is in the y direction, only one direction, right? Or else sometimes the heat conduction may be in the radial direction also. So that is also in one dimension, which is in the radial direction. So when it is in one dimension linearly, you have to use this, and when it is in radial direction, like when you take it in a cylindrical heat conduction or when you take it in the spherical heat conduction, so that time rate at which heat is transferred, you are taking minus Ka dt by dr. Okay, clear? Right. So using this, we'll try to make some of the questions. Okay, and we'll try to solve some of the questions, right? Okay. So starting with the question on the, which is also based on the both calorimetry also as well as the heat transfer. This is actually our thermal properties of matter, in that calorimetry is there and also heat transfer is also there. Right, here we go. A container with 1 kg of water is in it is kept in sunlight, which causes the water to get warmer than the surroundings. Right. Okay. The average energy per unit time per unit area received due to the sunlight is 700 watt per meter square, and it is absorbed by the water over an effective area of 0.05 meter square. Assuming that the heat loss from the water to the surroundings is governed by Newton's law of cooling, the difference in degrees Celsius in the temperature of water and the surroundings after a long time they are asking. Okay, so take 1 or 2 minutes time and just see the question properly. So just go through the question properly. So heat is simultaneously absorbed due to sunlight, and also it is losing also to the surroundings, which is governed by the Newton's law of cooling. and after a long time there will be some difference in temperature. So what is the exact concept? So most of the time it will be, you are using the fact that the temperature difference you are getting constant between the water and the surroundings. It is not, see, the water is not coming to the surroundings temperature. So there is a temperature difference between the water and surroundings after a long time. Why? Because simultaneously it is absorbing the heat from the sunlight and simultaneously it is losing the heat to the surroundings, right? So here we go, the same concept what we are applying. So what rate it is absorbing? 700 watt per meter square, and area of the plate is 0.05. So total heat what it is absorbing is 700 into 0.05, because it is per meter square and the total area of the plate is 0.05. This is the total heat what the water is absorbing per second, and the same heat whatever it is absorbing is equal to heat loss, right? Heat loss to the surroundings. So whatever the heat that it is losing to the surroundings, okay, right? Now how do you find this heat loss to the surroundings? So heat loss to the surroundings will be governed by the Newton's law of cooling. Okay, in the Newton's law of cooling, we know that minus dt by dt rate of cooling is equal to Newton's cooling constant into temperature difference. Okay, T minus T naught. This is the temperature of the water and this is the temperature of the surroundings. So this is after long time. After long time, whatever the rate at which it is cooling is equal to Newton's cooling constant into T minus T naught. Okay, but we want heat loss. Okay, so this is dq by dt. So we know that water dq is equal to ms dt, right? For the water, dq is equal to ms dt. So dq by dt is equal to ms dt by dt. And since it is losing the heat, whatever the heat it is losing, so minus of this, and minus dt by dt is nothing but rate of cooling. So from here you can substitute, because this is actually dq by dt. So dq by dt is equal to ms into minus dt by dt. Minus dt by dt you can substitute nicely, n into t minus t naught. Okay, so that is equal to 700 into 0.05. So from here already they have given this Newton's cooling constant, which is 0.001, right? And they have also given the specific heat of water, okay, which is heat capacity. Mass, this total is called as heat capacity of the water, 4200. So 4200 into Newton's cooling constant 0.001 into T minus T naught, that's the temperature difference. Okay, so this will be 35. Okay, so from here what is T minus T naught? That's what they are asking. Heat loss from the water to the surroundings and what is the temperature difference, right? So how much you are going to get? So T minus T naught, you are going to get it as, so 35.4.2. Take it. So around the nearest integer you can make it, right? So close to 8.3. That is the temperature difference. Okay. So here we are using completely the Newton's law of cooling, right? Minus dt by dt is equal to n times T minus T naught. So simultaneously it is absorbing also from the sunlight and also simultaneously it is releasing, it is losing the heat also, and heat loss dq by dt. From here this one directly you are taking, and most of the time your Newton's law of cooling, from how you are able to get, so actually dq by dt is equal to sigma ae T minus T naught. Okay. So T power 4 minus T naught power 4, sigma ae into T power 4 minus, because this is actually from Stefan-Boltzmann's law. From the Stefan-Boltzmann's law, if the temperature difference is very small, you are able to get the dq by dt directly proportional to the T minus T naught. Okay, hope you know that particular derivation. Okay, so this is a first question. Okay, we'll go to the next one. right? So here is another question. A water cooler of storage capacity 120 liters. So this is a water cooler. So total it is having a storage of 120 liters. Okay, it is having a storage of 120 liters. Can cool the water at a constant rate of P watts. So this can cool at a constant rate of P watts. Means it can give out the heat at a constant rate of P watts. In a closed circulation system as shown schematically in the figure, the water from the cooler is used to cool an external device. Here is an external device, right? So there is some external device which keeps on getting heated up and you want to cool this. How you can cool this? You have to feed the cool water to this device, okay, and the hot water is coming back, right? Because it is getting the heat, it is continuously getting some heat, right? The external device that generates constantly 3 kilowatts of heat. So this will get constantly 3 kilowatts of heat. 3 kilowatts. Continuously it is getting 3 kilowatts of heat. Okay, that is a thermal load, what we call, right? The temperature of the water fed into the device cannot exceed 30 degrees. So when the cool water is going into this, okay, because of this heat, whatever is coming, the cool water is getting heated up. And that cool water, whatever is getting heated up, that temperature should not exceed 30 degrees. So once it is exceeding 30 degrees, it will come out here and again it will cool and again the cool water is going like this. So that is a completely circulation, right? Generates constantly 3 kilowatts of heat. Okay. So the temperature of the water fed into the device cannot exceed 30 degrees Celsius and the entire stored 120 liters of water is initially cooled to 10 degrees. Initially it was at 10 degrees. Initially it was at 10 degrees Celsius. The entire system is thermally insulated. The minimum value of P in watts for which the device can be operated for 3 hours. So this will remove the heat at a rate of P watts, right? So completely if you take this as a system, in this total system, here 3 kilowatts is entering and it is removing at P watts. And initially already water is there at 10 degrees Celsius, right? So what is the minimum value of P in watts for which the device can be operated for total of 3 hours? So device has to be operated for 3 hours. So after 3 hours, what will happen is the entire water which was at 10 degrees, right, will go to 30 degrees. So here the main logic, if you check, heat, whatever is coming into the system is 3 kilowatts and rate at which you are removing the heat is P watts, which will be definitely less than the 3. Then only the total water is getting heated up slowly, and in 3 hours all this water initially which was at 10 degrees Celsius, all this water will come to 30 degrees Celsius, okay, because it was not removing the heat at the same rate what it is getting. So definitely the answer should be less than 3 kilowatts, so that we have to check it. So maybe the options may be out of A, B, C, it can't be D, right? Okay, so because they are asking continuously for 3 hours. So heat entering into the system 3 kilowatts, heat leaving out from the system P, right? So that was 3 kilowatts, means you can take 3000 minus this is P, okay, into how much time you have to operate? 3 hours. So 3 hours means 3 into, okay, this is watts, so each are 3600 power into time, right? So that much energy will be added up into the system. Because of that much energy which is added up into the system, the water initially which was at 120 liters of water which was at 10 degrees Celsius will rise to 30 degrees Celsius. After that you cannot operate this device. Okay, just getting my point? Okay, so that means in this particular time of 3 hours, the water, total water which is 120 liters of water which was at 10 degrees Celsius earlier will be exactly heated up to 30 degrees Celsius. So ms delta theta, right? So this is the total heat which is given into the system in 3 hours. Net heat, of course heat is giving, it is losing also, taking all, removing also, but net, so which is equal to ms. So 120 liters of water is 120 kg into specific heat of water, okay, already given 4.2 kilojoules, so take 4200 into delta theta, it is increasing its temperature from 10 to 30, so increase is 30. That's all. So you can calculate the value of P. Okay. So this is a only in single step. So only thing is you are understanding the question properly. Okay, what exactly is happening there? Okay, so check it. So you will be getting the answer like 3000 minus P is equal to 120 not to be like, so it will be definitely less than 3000. Anybody? So P value nearing about 2000, 2066.66 you will get. So 2067 you are going to get. Right. So we'll move on to the next question. A metal rod AB of length 10x has one of its one end A in ice at 0 degrees Celsius and the other end B in water at 100 degrees Celsius. Okay. If a point P on the rod is maintained at 400 degrees Celsius, then it is found that equal amount of water and ice evaporate and melt per unit time. So whatever the amount of water that is evaporating per unit time, same amount of ice also will melt per unit time. The latent heat of evaporation of water is 540 calories per gram and latent heat of melting of ice is 80 calories per gram. If the point P is at a distance of some lambda x from the ice end A, find the value of lambda. Okay. So just take 2 minutes, try to solve this question, all of you. Equation along with calorimetry. So again multi-conceptual. So there is a midpoint, some point at that point which is maintained. See, most of the problems in heat transfer, they will be giving you at a particular points are maintained at a particular temperature, right? So it is all about steady state heat conduction only. Whatever the heat conduction we are taking, that is a steady state heat conduction equations. Come on. Right. All right. So there is a metal rod AB of length 10x has one in ice. So here is one end and here is the other end. So one end is in ice at 0 degrees. So even though the ice is melting, so the temperature will be same, which will be 0 degrees only. And the other end, you can take water is at 100 degrees. And here is a rod, which is of course laterally insulated. So it should be insulated laterally so that heat is transferred only in the one dimension, right, along the length of the rod. Okay. Now there is a point P. So here you can take one point P. You can take a burner like this. You are heating it. Okay. So this has to be maintained at 400 degrees Celsius. This is 0 and this is 100, right? Now, definitely heat is flowing in this direction also, heat is flowing in this direction also, right? So let us say this is H1, this is H2. Rate at which heat is transferred in this direction is H1, in this direction is H2, and these two are not equal. Okay, but when H1 is flowing in this direction, definitely ice will melt, and when H2 is flowing in this direction, water is also evaporating. They have given how much ice will melt per second is same as how much water that is going to evaporate per second. See, most of the time in our heat transfer, we are going to use like dq by dt is the rate at which heat is transferred, which is equal to, in thermal conduction, we are using minus Ka dt by dx, right? And if at all this heat is transferred to some temperature, some object, and the temperature of the object is increasing, then you can write this as, because Q is equal to ms delta theta. Suppose if it is the same heat is transferred to some object and the object temperature will increase, so you can use dq is equal to ms dt, and I'll take delta t. So differential form dq is equal to ms dt. So dq by dt is equal to ms into dt by dt. This one when temperature is increasing. At what rate you are transferring the heat is equal to ms into dt by dt, temperature of the object keeps on increasing with respect to time. Suppose if the temperature is not increasing, rather the state is changing, right? The state is changing, so that time you know that Q is equal to ml. That time mass, suppose if ice is melting, so at what rate heat is transferred, so that time you will be calling rate at which heat is transferred is equal to capital L. That is the latent heat of, it can be either latent heat of fusion or it can be either latent heat of vaporization into dm by dt, right or not? So dq by dt will depend, dm by dt will depend on dq by dt. Now we are using, in this problem we are using this one, dq by dt is equal to L into dm by dt. So what rate heat is transferred is equal to latent heat into dm by dt, right? Okay, so here ice will melt, here water will evaporate, but whatever the dm by dt here and whatever the dm by dt here is same according to the question. Okay, equal amounts of water and ice evaporate and melt per unit time. Okay, under such situations, what is this? Suppose this length is x1 and this length is x2. They are asking x1 and x2, right? Okay. Now, whatever the rate at which heat is transferred according to this, so you are writing this equation. So K, same rod, same area of cross section, except the lengths are different. K into A into temperature difference 400 minus 0 by length is equal to dq by dt in this direction, right, which is H1. That is equal to L into, L is latent heat of fusion of ice, latent heat of ice. How much is given? Latent heat of melting 80. Okay, so you can put 80 here into dm by dt. First step, is it clear? So this is a step what we are using. L into dm by dt is dq by dt, and dq by dt is nothing but heat conduction Ka delta theta by L. Okay. Similarly, in this direction also, when the heat is flowing, right, and that rate at which heat is transferred is again Ka, same rod, same K, same area, but the temperature difference here is 400 minus 100, 300 by, here your length is x2 is equal to L into dm by dt. Now L is what? Latent heat of vaporization. So what is the latent heat of vaporization of water? It is given that it is 540. So we take 540 into dm by dt of this one. And this dm by dt and this dm by dt are equal, right? So you can simply divide and cancel this dm by dt. So Ka also cancels. So your equation will reduce to 4x2 by 3x1 is equal to 8 by 50. From here we can get the value for x2 by x1, or simply you can get only the x1 also, right? Because total length is 10x, so you can get that particular ratio. Okay. I think you will be getting 1 by 9. Okay. So x2 by x1 is something like 1 by 9. So already they have given total as 10x, right? So x1 is will be 9x then. Okay, this one will be 9x and this one will be, right? Okay. So this is a question which is relating your calorimetry also, heat transfer also by the conduction, right? Okay. And some of the questions in this also we'll be getting like this. See, they'll be asking us to find the temperature of a particular junction, right? So two rods are there, something like this, two rods. So here some values K1, A1 and L1, here some values K2, A2 and L2, and here some temperature maintained, here some other temperature maintained. Okay, always a possibility of asking the question, what is the temperature of this particular junction under steady state. So under steady state, whatever the rate at which heat is transferred from here to here is same as rate at which heat is transferred from here to here. So you are always using the expression, if the temperature of the junction is T, so whatever the rate at which heat is transferred from here to here is equal to, you can write temperature difference by thermal resistance, if you call it as Z1, thermal resistance. And the same thing, rate at which heat is transferred from here to here, T minus T2 by thermal resistance Z2. And the thermal resistance is always equal to L by Ka. Okay, so use this and you can get the value for T also, right? So in this model also, you will be getting the some of the questions, right? Or sometimes they will be giving you here ice, okay, and here 100 degrees it is maintained and here ice is given, and they will be giving you rate of melting of ice, and that time they will be asking you the temperature of the junction, that one also. So some value will be missing, K1 and K2 ratios. In this model, lot of questions which can be asked. So that time also, whatever the rate at which heat is transferred from here to here, suppose if I am taking here ice at 0 degrees and we are interested to find at what rate ice will melt, right? So rate at which ice is melting is nothing but, first you find out rate at which heat is transferred from here to here. So here to here rate at which heat is transferred is nothing but T1 minus T2 temperature difference by this resistance plus this resistance and Z1 plus Z2. Rate at which heat is transferred from here to here is equal to temperature difference by thermal resistance of this total, which is this resistance plus this resistance, Z1 plus Z2, because these two are in series, right? So that is equal to L times dm by dt. From here you can get the rate of melting of the ice. Same concept with two rods also, two different rods. So only thing you can have the series. So what is the difference between the previous question and this question? Here already we are using two rods, right? Two different rods, and we are talking about the temperature of the junction. Earlier problem, only we have used only one rod, and in some part of the rod we are maintaining at a particular temperature, both sides the heat was transferring, correct? Okay, right. And further, instead of using like this, you can also use a rod. One empty slide. Some more questions will be, so I am taking like this rod where area is changing, right? Here it is T1, here it is T2, and steady state, K is there, uniform, okay, length is L, and of course area is keep on changing, area of cross section is changing. So whether it can be like this, or sometimes the rod is uniform, area is uniform, and K value is changing, whatever may be the variable that can change, but rate at which heat is transferred is always same. So whatever the rate at which heat is transferred, here if you take 2 points, first point and second point, at one section and second section, okay, so dq by dt rate at which heat is transferred across first section and second section, okay, which is greater, which is less. So that we have to find. Similarly, areas, we know which area is more and which area is less. Similarly, dt by dx. dt by dx is nothing but temperature gradient first section and temperature gradient across the second section. First of all, across first section or second section, how much heat is transferred from here to here? Same heat will be transferred from here to here. Both of them are same. The rate at which heat is transferred from across first section and second section, both of them are same. But what about the temperature gradient? We know that dq by dt is equal to Ka dt by dx minus Ka dt by dx, correct? Now K is same, so area into dt by dx should be constant because dq by dt is constant. So already area here less, so that is why temperature gradient will be more. Okay, something like a continuity equation. So in the continuity equation also, area into velocity. So this you treat it like a velocity, and this area into velocity is a constant. So these things will apply in 3 chapters. One is in heat transfer, one is in current electricity also, right? And the other one is in fluid mechanics, something like a continuity equation. So here we are talking about what rate heat is transferred here and here same. And same thing in the current electricity, current is same through both the sections. And in the fluid mechanics, when you take this as a pipe and water is flowing, right? So how much volume of water here crossing and here crossing same, because water cannot be accumulated. Same thing, heat cannot be accumulated. Okay, same thing, charges cannot be accumulated. Correct or not? So it's something like a steady state over there. Okay, all right. So where is the temperature gradient more, where is it is less? Now they will give you what is the rate at which heat is transferred from here to here finally. So what is your procedure? Always it is better to use this differential equation in which this is constant, dq by dt is always a constant, which you can call it as h. Okay, you want to find h, but you just keep it as a constant because dq by dt from here to here it is a constant value. So keep it as h. Finally you have to calculate the h value only. So minus K A. A means take one small strip here, take a small strip which is at a distance of x and dx, right? So here the radius may be some smaller, okay, area will be pi r square, right, into dt by dx. So here what you have to do is, only thing is you have to write a radius in terms of x. That you can do it with a simple geometry, right? Because the radius is increasing uniformly from A to B. So you can draw one graph. So radius is increasing uniformly with length from A to B, right? Over a length L. So you can take this equation of this straight line, right? So you'll get radius in terms of x, that you have to put it here and complete. H is constant, K is constant. So this you are writing in terms of x. So dx by and x one side, okay, differential equation you are solving, dx and x one side, dt other side, and substituting the limits x0 t1, x equal to 0 t1, x equal to L t2. Finally you will be getting, after substituting those limits, okay, you will be getting the equation. From that again you subject this h, you take it out, that h one side, remaining all terms you take it other side. So you will get the answer for that. Okay, the same thing is applicable. Sometimes area may be constant, k is a function of x. So they will give you k as a function of x. So k is equal to something like k1 x plus k2 like that. So here also you substitute k as a function of x. Again same procedure. H is a constant, keep it silent. Okay, so then this is already k is a function of x, dx and x one side, dt other side, right? And integrate both sides with substituting the limits. Again at x equal to 0 temperature is T1, x equal to L temperature is T2. Okay, after substituting that, again take back the h value, one side take h one side, remaining all other sides. You will get the h value, because finally you have to find the h only. So like that, so that's such an important equation. in the heat transfer, minus Ka dt by dx. Okay, if it is in the linear. All right. Further, we'll take what already we have discussed. Right. So now coming into the some of the questions in the thermodynamics, one of the very important chapter. Okay. So in thermodynamics also, most of the time you will be expecting a more than one correct answer questions or numericals also, even the comprehension type of questions also very common in the thermodynamics, right? So we'll start working on that. See what points we have to remember in thermodynamics. So what are the important points that we have to remember? First we'll see that, okay. After that we'll start working out the problems, okay. Right. So in this, first, whenever equation is given, okay, the equation can be given either in terms of pressure volume or temperature volume or pressure or temperature, any equation, right? So please try to convert in terms of pressure and volume. Okay, you know how to convert by using ideal gas equation, right? Suppose even if they give you something like T into V cube is equal to constant, they did not give in terms of PV, but still you know how to convert into PV, right? So T, so temperature is nothing but PV by NR into V cube is equal to constant. Actually, it is nothing but PV power 4 is equal to constant, right? Like that you can always convert. So in that way, if you have converted something like PV power x equal to constant, any equation if you are able to have PV power x equal to constant, and if they are giving two temperatures T1 and T2, over all the problems you can solve, like they will be asking you heat transferred, change in internal energy or work done, or even in that particular process what is the molar specific heat in that particular process, right? So these are the four parameters. The equation is given and temperatures are given T1, T2 over, okay. Anything they ask, you can make it. Like change in internal energy is always equal to NCV delta T for any process which is PV power x equal to constant. Temperature changes, internal energy will be changing, because whatever we are seeing in thermodynamics, first of thermodynamics is only for a closed system, right? As long as a closed system, number of moles are same, right? Okay. And similarly, so work done is always equal to, you will take integral PdV. And if you are able to write PV power x equal to constant when the temperatures are changing from T1 to T2, this can also be written as NR delta T by 1 minus x. All right, NR delta T by 1 minus x. And the third one, you want to find the Q, heat. So that time, you are simply taking NC delta T, where C is a molar specific heat in that particular process. Right. In each and every process, molar specific heat will be different. Like in this particular process, molar specific heat again depends on the value of x and also the which type of gas you are using. Suppose if you are using monoatomic gas, okay, monoatomic gas also molar specific heat again depends on the process in which you are supplying the heat. So like C value is always equal to Cv plus R by 1 minus x. Okay. So this is a molar specific heat in that particular process. This is the fourth formula. And if you can make out these four, most of the problems easily you can solve. So your thing, your try should be like you are able to convert the equation into PV power x and check whether the temperatures are given or not. If temperatures are given, anything they can ask you, right? Any process you should be in a position. See, for any process, it can be given like theoretically also, it can be given like a graph also, right? For any process, we should be able to calculate what is the heat transferred, what is the work done, what is the change in internal energy. And if at all in that particular process, what is the molar specific heat for that particular process also, right? Okay. And yeah, one more thing also I would like to tell you in this thermodynamics. And whenever the questions are coming in the graphs, actually they are the easiest questions in thermodynamics when you get the questions on graphs, Okay. So because whatever they will try to frame, because we know these things nicely, work done in each process, we know the work done in each process. Heat transferred, any process, right? Okay. Now, one more thing is, we have to observe that, see, they will be asking you in a particular process whether heat is absorbed or heat is rejected. Okay, or they will be asking you in a particular process whether the internal energy is increasing or decreasing. So they just simply by looking at the equation, we should be able to tell whether, okay, if at all volume is increasing, if at all work done is positive, delta U is what or Q is what, because any of the combinations can happen when Q is equal to delta U plus W, right? So anything can be positive, anything can be negative. How to make out of that? So first, your isothermal lines. So whenever you have isothermal lines, they are all like this rectangular hyperbolas nicely. Okay. And whenever you are going along with this line, definitely temperature will remain constant. Now, if you are here and if you go like this, definitely T1, T2, T3, T4, T5, T6. We know as you are going like this, temperature is increasing. T6 greater than T5 greater than T4 greater than T3, T2 greater than T1, right? Now, whenever you go like this, you are touching this, so that means automatically temperature is increasing. So if you go like this only, temperature is constant. Okay, suppose if you are here, if you go like this, of course temperature will increase. Even if you are going like this, also temperature is increasing. Okay, because for isothermal line, PV is equal to constant. But if you are going like this, the value of X is, if you go like this, the value of X is 1, right? If you think that PV power X is equal to constant. Okay, so if you go like this isothermal, the value of X is 1. But if you are going like this, means value of X is less than 1. Okay, 0 to 1 means you will get this curve, right? X equal to 0 means you will get like this. Okay, X equal to 1 means isothermal, you will get like this only, temperature constant. And X is greater than 1, you will get like this. Automatically temperature will decrease when the volume is increasing, right? When the volume is increasing, expansion only, all these are expansions. So temperature will decrease. And even if you are going like this also, temperature will decrease on. So like that in the mind, though the isothermal lines will not be given, but by looking at these graphs, so in the mind inside that isothermal lines are also there. So how the curve was going, how the process is taking place, accordingly we may be able to get whether the temperature is increasing or decreasing, right? Okay. Using this one, any process, if it is PV power X equal to constant, we will categorize into 7. Okay. By looking at the polytropic also, right? So totally, suppose if the initial state is here, okay, so total 7 processes I will draw. 1, 2, 3, 4, 3, 6, 7. So each and every process, what is the importance of that? All are expansion except this, right? All these are expansions only. When the volume is increasing, what happens? Except this one. Of course, this is a constant volume, right? This I will take it as first one. All right, and we are naming as PV power X equal to constant. PV power X equal to constant. When we are talking about the X values, right? So first process, okay, is definitely X equal to 0, isobaric. Third process I will take X equal to 1, isothermal. Fifth process I will take X equal to gamma, adiabatic, and seventh process X equal to infinity. These are the values of X. And in between there are 3 other processes, and what will be that? So definitely X can be between 0 and 1 also. and here x is between 1 and gamma. This is very important, between 1 and gamma in the value of x. And of course, when the value of x is greater than gamma but less than infinite. So as the value of x is increasing, steepness of the curve also will increase, right? So steepness of the curve is also increasing because the slope will definitely depend on the value of x only, correct? Okay. So here 0 to 1, and here 1 to gamma, and here gamma to infinity and infinity. All right. Okay. Simple. Now for any process, what is Q, delta U, W, and molar specific. Okay. And which process you are talking about? First one, second one, third one. So first one, process. So first one, as you know, pressure constant, isobaric. First one is isobaric. Okay. So third one is isothermal. Fifth one, adiabatic. First one, third one, fifth one, and seventh one, isochoric. This we know. Okay. Next, in between also there are processes are there. Second is also there. Fourth process, some sixth process are also there, which are called as polytropic, some polytropic process in which the value of x will be 0 to 1 or 1 to gamma, right? All these things, right? Yes. In all these expansions, first, which are the things that are going to be 0? Isothermal, okay, delta U is 0. Adiabatic, Q is 0. Isochoric, work done is 0. Right? These three here. Next, your isobaric and another process is there, no? Where x is 0 to 1. In these two, these are above this, above the isothermal. These two are correct. When these two processes are above this isothermal, as I told you, isotherms are like this. So you are going like this means definitely temperature will increase. Okay, for these two, temperature will increase when the volume is increasing on expansion. So that is why, and before that, all work done are positive only. Positive, positive, positive. All work done are positive except this isochoric, which is 0. Here the fourth one, I will call it as 1 to gamma. And of course, sixth one, gamma to infinity. Right? Okay. All are positive. Up for expansion. For compression, it will be reverse. Okay. Delta U, simple. Isothermal 0, no? Above this, take positive. These two. And below this, all delta U will be negative, 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 negative. Simple. Okay. Next, here 0. Above this, work done positive, delta U positive. So automatically Q is also positive. Okay. So these two positive, Q is positive. Means heat is absorbed by the system. Internal energy increase, work done also done by the system. Nice. So here also these two positive, this is also positive. 0 and positive, definitely positive. Only problem comes here. Okay, negative delta U plus W, because most of our questions will be, they will be giving in such a way that the value of x will be in between 1 and gamma, or sometimes it will be gamma and infinity. So you will find like you will observe that okay, volume is increasing, so W is positive, that's fine, and temperature decreasing, so delta U is negative. So negative and positive, so again you cannot make all of a sudden Q. But adiabatic it is 0, above adiabatic it will be positive. Above adiabatic positive and below adiabatic it will be negative. That's all. And mostly they will be touching this fourth one and sixth one. We should be knowing, because see this minus plus and here plus, minus plus but minus. Okay. So you only have to check is the value of x is less than gamma or greater than gamma. Okay, greater than gamma how it behaves, less than gamma how it behaves. And now when we also come to the molar specific heat, okay, so Q is equal to NC delta T, where C is a molar specific heat in that particular process. So molar specific heat is equal to, okay, so Q by N into delta T. Okay, so Q positive, delta T positive means C is positive. So Q positive, delta T means you can take delta U only, correct? So delta T means delta U. So Q positive, delta U positive, because delta T positive only, delta U will be positive. So these two positive, so molar specific heat positive value. What does it mean that molar specific heat is positive? When heat is absorbed by a system, its temperature will increase. In the same way, when heat is rejected by a system, its temperature will decrease. Reverse will not happen. Reverse means when heat is absorbed also temperature decreases. Then that means even though heat is absorbing, temperature can decrease. That means that molar specific heat of that particular process is negative. Molar specific heat in that particular process is negative. When heat is absorbed also and still temperature will decrease. That happens. Okay. So here also it is positive. And isothermal, okay, here Q and delta U, so this will be infinite, tending to infinity, isothermal process. Okay. And in fact, isobaric it is positive and Cp. And isochoric, so see this isochoric, Q by delta U. So Q by delta U, negative, negative, so it will be positive, it has to be. So because its value is Cv. Right? Adiabatic, Q0, okay, delta U is there, but Q0, so here you will get 0. So things are only this one and this one. Okay. So here what you will get, Q by delta U. Q by delta U. What is this? So definitely it is negative in this process. Fourth one, molar specific heat will be negative, and in the sixth one again it will be positive. So please check, there is only one process in which the molar specific heat value will be negative when X is lying from 1 to gamma. This you have to check. Right? Gamma is the adiabatic index, right? So something like they will give you monoatomic gas. Okay, monoatomic gas. Actually, gamma value is 5 by 3. Okay, 1.66. Right? They will give you something like 1.4 is equal to constant. For monoatomic gas is expanded according to PV power 1.4 is equal to constant. It is expanded, right? So it's expanded means volume will increase. Okay, and is the value of X less than gamma? Yes. And greater than 1? Yes. Right. So here work done, it is expanded, so work done is positive. Right. And what is Q and what is delta U and what is C? Immediately you can tell that even though it is expanded, but its temperature will decrease. Even though you are supplying the heat, heat is absorbed only. So in this case, even though it will absorb the heat also, its temperature will decrease. Means suppose its temperature is decreased, means its internal energy also it is losing. Means something like 70 calories it is absorbing and it is losing 30 calories of internal energy also. Totally it will do 100 calories of work. Right or not? So like that it will do the 100 calories of work. So that is the case when molar specific heat is negative. So it will absorb the heat also. It will also decrease its internal energy also. Both it will utilize to do the work done only. Right? Okay. So like that. So if you remember this table and the main concept, okay, of this table. So what is expansions? In all the cases I have taken the expansions only. Reverse will be compressions, right? So most of the time these processes only will be there. This generalized table what we can make out. Okay. Hope this is clear. Right. So we'll go to the further whatever the concepts we have learned so far. So we'll be doing some problems on the thermodynamics also, right? Hope all of you are ready. Okay. Start. Read this, go through this question. Consider 1 mole of helium gas enclosed in a container at initial pressure P1 and volume V1. It expands isothermally to volume 4V1 isothermally. After this, the gas expands adiabatically also and its volume becomes 32V1. Then work done by the gas during isothermal and adiabatic expansion process. Both of them are expansion. So make a graph also. This is a PV graph. First it is expanding isothermally. Initially its volume was V1. Okay. So let it expand like this. Right. After this it is expanding adiabatically. So steep. Correct. Okay, initially the volume was V1. This you can take it as V1. So you can take it as 4V1 and finally 32V1. Okay, any pressures? Initial pressure is P1. This pressure is P1. So since it is isothermal, so volume is becoming 4 times. So definitely pressure will be 1 by 4 because it's an isothermal process, right? So take this as state 1, this state 2 and this state 3. Simply they are asking what is the work done in this process and work done in this process. 2 work done they are asking. Okay, how do you find? So work done in isothermal process. You should find also work done in adiabatic process also you need to find. Okay. So work done in isothermal process is always equal to nRT ln V2 by V1. But temperatures are not given, right? So nRT is same as either you take P1 V1 or P2 V2, which is same as P1 V1 only. So this you can write it as P1 V1 only, because whatever the product of P1 V1 here and here, it is same. Ln of V2 by V1. So this volume by this volume, how much? You will get 4. This is a work done. Simple. So in isothermal process, straightforward question. And even if they ask you heat also from 1 to 2, Q also is same actually. Q and work done, both of them are same in the isothermal process from 1 to 2. Now we talk about adiabatic process. Adiabatic process, what are the things that we can use in the work done? So for the work done in adiabatic process, in the adiabatic process, whatever the work done, that is actually given by nR delta T by 1 minus gamma. It is simply equal to minus of delta U, and delta U is NCV delta T. So minus of NCV delta T. CV is R by gamma minus 1. So that is by nR delta T by 1 minus gamma. But temperatures are not given again, right? So you can write it as nR into T2 minus T1 by 1 minus gamma. T2 minus T1 by 1 minus gamma, right? So T2 you can write in terms of nR. What is nR T2? P2 V2. Okay. In fact, so it is expanding from 2 to 3, no? Okay, better 2 to 3 means, so I'll correct it to T3 minus T2, more clear. Because this is a third, this is a second. Right. That was a formula just. Right. So what is nR T3? P3 V3 minus nR T2 is P2 V2 by 1 minus gamma, and helium gas 1 mole monatomic. So what is the gamma value for helium gas? Monatomic 5 by 3. So substitute that. P3. So what is this pressure? They did not give P3. P2 they have given, and V2 and V3 they have given anyway. So what is P3? So from adiabatic relation between the pressure and volume, so PV power gamma is equal to constant at, because it's equal to constant. So you can write pressure at 2, which is P1 by 4, into volume at 2, 4V1 whole power gamma. PV power gamma is equal to constant. Okay, so PV power gamma at 2 and PV power gamma at 3. So this is equal to pressure at 3, which we don't know, into volume 32V1 whole power gamma. Gamma is 5 by 3. From here you can calculate what is P3, right? And the same P3 you can substitute there. P3 is there, P2 V2. So this also you will be getting in terms of P1 V1 and all, right? So P3 will be P1 by upon 4 into 4V1 by 32V1 whole power gamma. So 1 by 8 whole power gamma, and the value of gamma is 5 by 3. Okay, so 1 by 8 whole power 1 by 3 is 1 by 2. So 1 by 32, 32 to P1 by 128, 32 4, yeah. Okay, so that is P3, right? So P3 is actually P1 by 128, and what is V3? V3 is 32V1 minus P2 V2, which is same as P1 V1, by 1 minus gamma 1 minus 5 by 3 minus 2 by 3. Okay, so 4. So P1 V1 by 4 minus P1 V1. Okay, so P1 V1 1 by 4 minus 1 minus 3 by 4 upon minus 2 by 3. I think so 9 by 8 P1 V1. Okay, right. So that was 9 by 8 P1 V1, and this was this one. This is the work done in adiabatic. They are simply asking the ratio isothermal by adiabatic. So this one, so by this one P1 V1 will get cancelled. So your answer is ln 4 by 9 by 8. So 8 by 8 ln 4. Ln 4 is 2 ln 2. Ln 2 is 0.693. All that is substitute. Get the answer to the nearest integer. Okay. Hope it is clear. So simple, starting with a simple question only. Okay, you are talking about work done. Nicely equations what we are using for the work done. Okay, right. Next one. Yeah. So here in this question also 2 moles are there, adiabatic process. So not an adiabatic process. 2 moles of monatomic ideal gas undergoes a thermodynamic process in which V cube by T square is constant. Some relation in terms of volume and temperature they have given. V cube by T square is constant, and if the temperature is raised by 300 Kelvin, delta T they have given. See, as I told you, whenever process is given and delta T is given, any question you can solve. Whether they are asking Q or whether they are asking delta U or work done, or whether they are asking molar specific heat, anything you can make it. Because delta T they have already given, change in temperature. Okay. So first let us try to convert this in terms of pressure and volume, power x. Okay. So V square by T square is equal to constant. Pressure and volume you have to convert. Okay, I will convert. So P square V square, because temperature directly proportional to PV is equal to constant. Come on. So P power minus 2 and V is equal to constant. Right, and this can also be called as PV power minus 1 by 2 is equal to constant. Means the value of x is actually minus 1 by 2. That's all. So once the value of x is minus 1 by 2, now whatever they may ask, like work done they are asking here. So work done is always equal to, whenever the equation is, I mean the thermodynamic process is given by PV power x equal to constant, work done is always given by nR delta T by 1 minus x. Okay, n is 2 moles, R delta T is 300 Kelvin by 1 minus x, x is minus 1 by 2. So 1 minus 1 by 2, 400 R. Option A correct. Then change in internal energy they are asking in CV delta T, 2 moles, CV value monatomic gas. So CV value PR by 2, delta T already given 300. Okay, so that is 900 R. And see here the value of x is negative. So when the value of x is negative, actually P directly proportional to root V, this one, isn't it? And definitely in this case, and they are saying that temperature is increasing. Temperature is increasing and pressure and volume, both of them are increasing. Pressure is increasing, volume is increasing, even temperature is also increasing. All three are increasing. So when all three are increasing, definitely work done will be positive only. Delta U is also positive only. Q is also positive only. They are not asking Q. Molar specific heat they are asking. Yes, molar specific heat is always given by CV plus R by 1 minus x for any process, which is represented like this, PV power x equal to constant. So what is CV value for monatomic? 3R by 2 plus R by 1 minus x is minus 1 by 2, okay, 3 by 2, so 2 by 3, 9, 13 R by 6, 13 R by 6 is correct. Change in internal 900 R, yes, correct. And if they are asking like Q also, which is nothing but delta U plus W, 1300 R is the Q value. Q also you can find out 1300 into R. All you made it. Just they have given the process, that too in terms of volume and temperature. You are able to find work done, delta U, molar specific heat also, and also Q value also, right? So simple model of the question when the process is given without any graph, right? Okay, hope all of you can make it these type of questions, right? All right, done. Next. Now the questions, some graph with the graph when pressure and temperature, not pressure and volume, right? Okay. So 1 mole of monatomic gas. 1 mole of monatomic gas is taken through a cyclic process shown in the figure. Temperature at A is 300 Kelvin. Okay, process AB is defined as PT is constant. There's a process AB like this, right? Which is some curve which is PT is equal to constant. Something like rectangular hyperbola for PT, not for PV, right? So it's like this, and this is the constant pressure, right? And this is passing through origin. Definitely pressure temperature passing through origin means that will be a constant volume. So Ca is isochoric constant volume, right? And they are giving temperature at A is 300 Kelvin. Yeah, temperature at A, right, 300 Kelvin. Okay. And since it is a PT is equal to constant, here to here if you observe, here to here pressure is increased by 3 times. So definitely temperature will decrease by 3 times. Automatically you will write here 100, 300 to 100. Why? Because PT is equal to constant. Pressure increase, so temperature has to decrease. And what about this one? So here it is a straight line passing through origin. So here to your pressure triple, so temperature also triple. Okay, so 3 times. So here also 3 times, put 900 over 3 times of 300. All the temperatures you have got. Okay, now what do you want to calculate? So here you can calculate so many things. Any process, every process you can find out what is Q, what is delta U, what is W also for any process. And also one more likely questions are like total efficiency of the cycle also can be asked here, right? Okay, first let us complete this, and after that some more we'll add to some more questions to that. Work done in process AB. Okay. AB process is pressure temperature, you know what to do. Okay, pressure into temperature is a constant, so try to find out pressure volume relation. Okay, so temperature PV, because PV is equal to nRT, so temperature directly proportional to PV, which is constant. So P square V is constant, means PV power 1 by 2 is equal to constant. X is 1 by 2. So work done nR delta T, because all the temperatures are given nicely. So first one, they are asking in the process AB, nR, N is 1 mole, R delta T. Okay. So AB process temperature is actually decreasing. So delta T is 100 minus 300 minus 200 by 1 minus X is 1 by 2. So this comes out to be minus 400 times R. Right. Option A correct. The change in internal energy, of course, in process AB you can find Q also, you can find delta U also. Every process you can find all three. Okay. Let me complete that. So work done you have found out, right? So try to find out. See, I'll do like this. Just forget about the question. So we'll frame it. So process AB. Okay. So what is the work done? Found out, yes. What is delta U? NCV delta T, 1 mole. CV, which gas? Monatomic, yes, 3R by 2. Delta T, temperature decreasing, so minus 200. Okay, that will be minus 300 R. Internal edge also decreases, work done is also negative. So Q is equal to delta U plus W, right? So add these to minus 700 R. Means heat is rejected in the process AB, heat is rejected in this particular process, right? That is process AB. Now let us come to process, which one you want? BC. Okay, let us come to the process BC. In the process BC, It is a nicely constant pressure process, isobaric, right? So what is the work done? Isobaric process, Nr delta T, Nr delta T here to here, what is the change? 900 minus 100, 800. That is 800 times R. And what about Q? NCP delta T, N Cp value, monoatomic gas, Cp value, pi R by 2, delta T 800. So we'll be getting 2000 times R. And what about delta U? N Cv, which is 3R by 2, delta T 800, 1200 R. And of course, delta U 1200 R plus W 800 R is equal to 2000 R, just cross checking. First law of thermodynamics. Okay. Next left out is Ca. Which process is Ca? Definitely is a constant volume. W is what? 0. Delta U, change in internal energy. NCV delta T. What is N? What is Cv? Delta T. Delta T from here to here, 900 to 300. So decrease. So minus 600. So what's the value here? Minus 900 R. Similarly, Q. So of course same minus 900 R, because Q is equal to delta U plus W, because work done is 0. Now let us check. Change in internal energy process Ca. Change in internal energy process minus 900 R, which is T. Heat transferred in the process BC, Q value 2000 R. Okay. See, I will add one more question to this. Since it is a cyclic process, no, whenever there is a cyclic process, always one more important question, that is the efficiency of that particular cycle. Okay, so that is very, very important, that efficiency. I'll show it here. Efficiency of the cycle. Efficiency of any thermodynamic cycle is nothing but net work net by heat absorbed. Not in all the process heat is absorbed, isn't it? But if you find the net work done, you have to add all the work done, right? Like here, what is the work done? Minus 400 R. Here, what is the work done? 800 R. And here, what is the work done? 0. So if you add all the work done, minus 400 R plus 800 R is 800. Sorry, minus 400 R plus 800 R is 400 R work done. And heat absorbed means only the positive values of heat only you have to take. Here, what is the heat? Negative. So heat is rejected. Don't take this. Here, 2000 R. And here also negative, so don't take this, only 2000 R. Okay, RR cancels, so one efficiency is what? 1 by 5 percentage, okay, into 100, 20%. This can be always a question. In any thermodynamic cycle, they give always, this will be a nice question. Efficiency of the thermodynamic cycle, okay. So we should practice, like whenever the graphs are given, every process, all three, whether they ask or not. So try to practice like all the three and find out the efficiencies also. Alright, okay. Next. So another questions are, you have a heat is being transferred and some compartments are there, piston is lifting, movable piston, sometimes not a movable piston, and like these are the other type of questions. So we'll see one or two questions on this also, right? Come on, go through the passage. In the figure, a container is shown to have a movable piston on top. So this is a movable, right? This is a movable piston. Confirm. Okay. The container and the piston are all made up of perfectly insulating material. Most of the time they will give you total, it is insulating only. Right? So this is a cylinder and the piston completely insulating. But the thing is, container is divided, this total container is divided into two compartments by rigid partition. Rigid, this is a rigid partition made of thermally conducting material. Thermally conducting material. So two things are possible here. Thermally conducting material means always here and here temperature should be same. Okay, finally the temperature has to become here and here should be same, thermally conducting material, right? So that is one thing. Okay, so that allows slow transfer of heat. The lower slow transfer. That is why initially if you put some different temperature, it takes some time to get adjusted to the common temperature. So lower compartment of the container is filled with 2 moles of an ideal gas, monoatomic gas, 700 Kelvin. Okay, So 2 moles mono 700 Kelvin. Done. Okay. And the upper compartment is filled with 2 moles. Which gas? Monatomic. Lower compartment 2 moles monatomic. Upper compartment 2 moles diatomic. Yes. So diatomic. And it is at 400 Kelvin. Right. And heat capacity is already given. We know that. What happens? See, if you just release like this, and this is a rigid. See, here 2 questions are possible. This is anyway movable. When this is a movable, always this pressure will be constant, because this pressure is exactly equal to the atmospheric pressure and whatever that mg is there, no, mg by area plus atmospheric pressure is equal to this pressure, because whichever compartment the piston is movable, always that pressure will be constant, because piston will move according to make sure that the pressure is constant. Of course, unless or until you have a spring here, then this pressure will not be constant, because when it is lifting, spring force will be more and more. So that is why to balance that pressure also will increase. That is a different issue. Otherwise, if there is no spring, there is only atmospheric pressure and some whatever the piston weight is also there, this pressure will be constant. Right. Now let us look at some questions on this. This is a passage. Okay. So we have given some questions. Now here, just if you leave it like this, what will happen? So this is a fixed, but this will allow the heat. This piston will not move, but this will allow the heat. So definitely this is a 700 Kelvin, this will lose the heat to this. So it will gain the heat, and the piston will lift up. Right, piston is also lifting up. So this is gaining the heat and piston is also lifting up. Right. So, but finally no heat is transferred to outside, that's for sure. No heat is being transferred to outside. It is giving the energy, it is taking the energy, and also it is doing the work. Because it is pushing the piston, it will do the work. Right. So let us see those questions. Look at that figure. Right. Right. First question in this. Consider the partition to be rigidly fixed so that it does not move. When equilibrium is achieved, final temperature of the gases will be. When equilibrium is achieved, what is the final temperature of the gases? So initially, this was a movable, I'll take it like this, movable piston, and this was fixed, right? Fixed. Right. Initially it was like this, and here it was mono, like 700 Kelvin and 400 Kelvin. This one initially. Finally, what happens? This will be like this only, because it is rigid, it won't move, but this may move. This may move because it's frictionless. This is what happens. But since it is a conducting, this temperature and this temperature should be definitely same. This is T, means this also will be T, compulsory. Both will be T. And that equilibrium is achieved. This is the equilibrium condition. So initially it is like this, just if you release like this will rise up, and until finally both temperatures are same. So when the equilibrium is achieved, final temperature of the gas. Come on, just 1 minute, I will try to give you the time anybody can solve. What is the final temperature of the gases when equilibrium is achieved? Very good question. So just think of the energy concept, total energy. So no energy is going waste, no energy is going outside. This will have some internal energy, this will also have some internal energy, right? Some of the internal energy it will give to this, and this internal, whatever it is taking the energy, some part it is doing the work also, right? So totally what was happening? So heat is going like this, right? Is it not giving out the heat? Yes. At constant volume, it is giving out the heat. So because it's not doing any work. This lower compartment gas is not doing any work. It is only giving out the heat at constant volume. It is giving out the heat, so that its temperature will decrease, its internal energy will decrease, and it is taking the heat, and its pressure is maintaining constant, means it is taking the heat at constant pressure. Whatever the heat it is giving, whatever the heat the lower compartment gas is giving to the upper compartment. So lower compartment is giving the heat, rejecting the heat at constant volume, and the upper compartment gas is taking the heat at constant pressure. Okay, exactly whatever the heat this will give, this will take. We can no more. Okay, right. So at what heat given by the lower compartment is got heat taken by the upper compartment. Okay, because of that, of course, its internal energy will change and it will do the work. That's a different issue. But first of all, heat given by the lower compartment at constant volume. So N 2 moles, CV monatomic gas, CV value 3R/2, and since it is giving out the heat, its temperature decreasing from 700 to T. So 700 minus T, NCV delta T. Heat lost by this monatomic, and same heat gained by the diatomic, and it is taking the heat at constant pressure. N CP, what is the CP value of diatomic gas? 7R/2 into delta T. It's increasing its temperature from 400 to T. So you have to write T minus 400. Heat loss equal to heat gain. Equate. Okay, so try to understand this. Whatever the heat this is losing, this is gaining the same amount of heat. So if you do this, minus 2800, 2049, so 3 10 by 10, 490. 490. So that is a step. Only thing is understanding the question, and just it's a simple only one step, but exactly trying to make out that. Okay. So here whenever the pistons are given, freely movable piston, pressure constant, and when it is a conducting piston, temperature on either side should be constant finally, because it's a conducting, right? So sometimes this also will be insulated, so definitely this will not give any heat, and it is movable means definitely it will push, it will do the work. In that way, that is also one more problem. That also I have taken one question on that also. Hope you have understood this. And in this second bit is also there, that one. Now consider the partition to be free to move without friction. Partition is also free to move, so that the pressure of the gas in both the compartments is the same. Then the total work done by the gases till they achieve equilibrium will be. This is another question. So initially it was like this. This was also movable. This was also movable. Okay. 700 Kelvin, 400 Kelvin. Mono diatomic initially. Just releasing like this. So what happens? This will also push, this will also push. See, finally, this pressure will always be that P naught plus mg by A, because to balance this. Okay, and same pressure this also will have. So finally, initially whatever the pressure this was having, finally also this will have the same pressure, and this will also have the same pressure. I mean, this is also movable, so this is also now giving out the heat at constant pressure. Earlier, this lower compartment gas was giving the heat at constant volume. Now it will give the heat at constant pressure. This will anyway taking the heat at constant pressure because it is a movable piston, right? So finally it may look like this. And in this question, nowhere it is mentioned like atmospheric pressure is not given, they are not asking any work done and all, right? Finally, they will come to temperature T and T. Now also it is losing the heat. Again, it is conducting only, so it will give the heat and it will take the heat. Now it is giving out the heat at constant pressure, and this is anyway taking the heat at constant pressure only. Then what will be the equilibrium temperatures? So let us find out that. Same thing, except here this is same, but here it will be also giving the heat at constant pressure only. So that means N Cp for monatomic gas, Cp value 5R/2, delta T 700 to T. Yeah, taking at constant pressure, heat taken by the upper compartment gas at constant pressure only. So N, okay, so Cp, for that it is actually 7R/2 because diatomic gas, and its temperature increasing from 400 to T, so T minus 400, same step. Only this is a change. 3500 minus 5T is equal to 70 minus 2800. 12T is equal to 1300. Okay. 525 Kelvin. Temperature is 525 Kelvin. So both the compartments, it will reach 525 Kelvin, and here also 525 Kelvin. But did they ask the temperatures? Final temperature? No, they did not ask the final temperature. They have asked the total work done by the gases till the time they achieve equilibrium. Definitely this will push the piston up, so this is doing the work, and this is also pushing the piston up, this is also doing the work. Finally, no heat is lost to outside, but they have moved. So whatever the work they have done, see, if you take this total as the system, did they lose any heat? No, they did not lose any heat, but they have lost their internal energies. And even this is also losing the internal energy. Definitely its temperature decreasing, it has lost its internal energy. Of course, this has gained its internal energy, no doubt. But also some work has been done externally, because no Q is anyway not there. Q is equal to delta U of the plus W. Total sum of Q for the total two gases is equal to change in energy of two gases plus work done by the two gases, right? And whatever the total change in internal energy of this gas and this gas will reflect in the form of work, because there is no heat which is rejected to outside. So what I do is work done by the total system, total work done by the gases they are asking, till the achieve the equilibrium. So total work done will be, first this gas will lose the internal energy, okay, so which is NCV, so monatomic gas 2 moles, N, what is the CV value? 3R by 2, delta T 700 and 525, okay, 175. This much internal energy it has lost, okay. This has gained some internal energy, N CV of the diatomic gas 5R by 2, delta T, so delta T 525 minus 400, so it will be 125. Okay, so this you are subtracting, because whatever it is losing, this is losing the internal energy, it is gaining the internal energy, plus some work is also doing, right? So net loss of internal energy, net loss, because one is losing, the other one is gaining. So net loss, that is only the work done by the system, two gases. So check it. 175 into 3, 525 minus 625 R minus 100. Okay, that is the work done. In fact, it is a negative only. The work done by the gases is actually negative, right? So that's what happens. Okay. So that means this piston may be coming down only, it's not going up. It's not necessary that it should go up, because temperature is increasing, volume may decrease also, right? So that is the total work done by the gases. So this is also a very good question, right? So here I made sure that when the piston was rigid, what happens, when the piston is movable also, what happens, and at the same time the partition was fixed, what happens, the partition was movable, what happens, and the partition is always a conducting, making sure that both the sides the temperature is same, okay, right. Now when you, another one more question, I will try to make it. So when the piston, the partition whatever you are taking is not conducting, rather it is also insulating, okay. Here is another question. Now you are also heating extra, right? So these two models, if you make it, no, so whenever these partition problems are there, it will become very easy for us, right? Now another passage, thermally insulating cylinder has a thermally insulating and frictionless movable with partition in the middle. So this is insulating, but it is movable, right? It is movable, so we have to make it properly. So I'll take this is joined, this is also joined. Mobile. Now you will come across like it is a mobile, and this can move, right? Right. Okay. On each side of the partition, there is 1 mole of an ideal gas. Specific it at constant volume. CV is equal to R, right? I think it's a polyatomic gas, right? And R is the gas constant. Initially, each side of the volume V0, temperature T0, V0, T0, same as it is. Same gas, same volume, same temperature, exact in the middle. Left side has an, but electric heater. Left side is having an electric heater, which is turned on at a very low power. Slowly it will supply the heat. Slowly, it may transfer also, because actually heat may not be transferred, but this will push the piston, so work will be transferred, correct? So that is what earlier in this question, earlier heat was transferred through the partition. Now partition is also insulated, so heat is not transferred from here to here, rather work will be transferred from here to here, correct? So that is the difference between the two passages. To transfer heat Q to the gas, this will give Q, give it on the left side. As a result, the partition moves slowly towards the right, reducing the right side volume to V0 by 2. Okay, right. So finally, this will move somewhere here. Okay. Consequently, the gas temperature on the left side and the right side becomes TL and TR. Here temperature will be TL and the right side will be TR. Ignore the changes in temperature of the cylinder, heater and the partition. Okay. No more heat is lost to the surroundings. Only you are supplying the heat. So it will move here and stop. Okay. Because you have transfer Q heat, right? Clear? Just look at the question carefully. And CV value is 2R. And so gamma value will become, okay, so what is the gamma value when CV is 2R? So CV is equal to R by gamma minus 1. CP is 3R, in fact. Yeah, better. CP is 3R. So gamma is 3 by 2. Okay. Polyatomic gas, the gamma value is 3 by 2. Right? So hope the passage is clear. Now we'll try to solve this. So when you supply heat Q to this, okay, so this will do some work. Its temperature also changes, so it will also doing the work. Volume changing, temperature changing, but here and here pressure will be same because it's a movable piston. No? So final pressure here and here should be compulsory. It should be same, and number of moles anyway here and here it is same, right? First question. Volume of TR and T0. T0 was initial volume. T0 initial volume. Final volume. Here TL and there TR. Okay. I'll change the figure also again. See. Initially it was like this. T0 V0. T0 V0. Okay. Finally it will be here. V0 by 2. Right side is V0 by 2. Okay. So right side is V0 by 2. Automatically left side will be 3V0 by 2. And temperatures, they are saying T left and T right. Temperatures are not same because it is not a conducting, but pressures are same because it is movable. Because it is movable, here and here pressures are same, but that this pressure is not equal to initial pressures. Mind you that. Okay. Initial pressures may be P1, P1. Final is P2, P2. This pressure is not same as this pressure, right? You are supplying the heat. Heat has transferred, and what has happened is this one. Now what are they asking? What is the temperature? See here also, if you just look at this adiabatic, okay, it is completely insulated and this is all insulated only. All this is insulated including this one. So this piston is pushed. So whatever the process that is taking place in this chamber is adiabatic, right? Piston is pushed. So whatever the process that is taking place in this exclusively, that is totally adiabatic because nowhere the heat is coming because this is insulating, right? And when the volume is decreasing from V0 to V0 by 2, automatically you will know the temperature also because in the adiabatic process you will know the relation between temperature and volume. What was the relation between temperature and volume? You have to remember this T power gamma minus 1 is a constant. So initially T0 V0 for gamma 3 by 2. So 3 by 2 minus 1, which is 1 by 2, is equal to final temperature, which I have to find, final volume V naught by 2 whole power gamma minus 1 again 1 by 2. So what is TR? V naught by 2. So is it not root 2 V T naught? Yes. So TR by T naught is root 2. Simple question. So here that idea should click, because you are supplying the heat, it is pushing. So this chamber, whatever is happening, that is an adiabatic completely, right? Okay. But here it is not adiabatic, because you are supplying the heat, it is pushing the piston, right? So heat is supplied also. Okay, it is pushing the piston, not a constant pressure also, not a constant volume also, not an adiabatic, not an isothermal for this chamber. What is the process that is happening? Some other process. Okay, so clear. Next, how much heat you have actually supplied? Next question in this. Next bit in this passage. The value of Q by RT naught. Okay, so this value, how much you have to find, right? So Q by RT naught, how much value is that? You need to find. So for that, go back. Whatever the heat you are giving here, how much heat you have given to this? You have given some heat, because of which its TL also changed, okay, and TR also changed. TR has increased, so you have to check for TL also. So how do you calculate the temperature? Because whatever the heat you have given here, it is utilized, no external work and no external heat loss. So only this internal energy has increased, its internal energy has also increased. Both internal energies have increased because of this Q. Because if you take total as one system, internally whatever may happen here, no issues. Whatever the heat you have supplied is utilized for increasing its internal energy and its internal energy also. You may think, sir, it is doing some work. So whatever the work it is doing, same negative work. So internally, when it is moving, this work, that work, need not have to consider at all. Clear? So heat is equal to increase in internal energy of the left plus increase in internal energy for the right. Right in increase in internal energy you can find because temperature you know, final temperature. But left side temperature also you have to find, no? How do you find the left side temperature? By equating the pressures, right? So since the pressures are same, here and here pressure is same, so pressure is equal to nRT by V. So pressure same, nR same, number of moles are same, temperature by volume is constant, right? So here temperature TL by what is the volume? 3 V naught by 2 is equal to right side, what is the temperature? Root 2 T naught by volume is V naught by 2. That's all. Okay. V naught by 2 cancel. So T left 3 root 2 times T. Okay. So equating the pressures on either side, because volume is 3 times, okay, pressures are same, so temperature also 3 times. Yes. Now delta U of the left, delta U is N NCV delta T. Both sides, what is the nature of the gas? Here you have taken 1 mole of an ideal gas only there, right? Okay, no problem. Just 1 mole of an ideal gas told. Delta U, N, already I think CV value they have given, okay, 2R into delta T. Delta T of the left is how much? So 3 root 2 T naught minus T naught. So 3 root 2 minus 1 T naught. Similarly, delta U for the right, N CV is 2R only, and root 2 T naught, root 2 minus 1 times T naught. So totally it becomes, coming here, solve 2R T naught, you take it common. 2R and T naught, you are taking common 2R T naught. So 3 root 2 minus 1, okay, plus root 2 minus 1. So that gives you 4 root 2 minus 2 into 2R T naught is the answer for total Q. They're asking, the question is, yeah, Q by RT naught. This question I am solving actually. Q by RT naught. So Q by RT naught. So Q by RT naught is equal to 2 and 2 common. If you take 4 into 2 root 2 minus 1. 4 times 2 root 2 minus 1. Okay. So 4 times 2 root 2 minus 1. Option B. Right. Take it. Like that, you will be getting this. These two passages, whatever we have taken, okay, making sure that one was conducting the previous passage and movable ones, fixed ones. Here you are taking adiabatic, partition and movable. Suppose if you take adiabatic and not movable, nothing will happen to this. Correct or not? So nobody will give you like fixed and adiabatic. So nothing will happen to this gas. Only you have to check only for this chamber. Correct? So that is how things will be there. Okay, so these are all the questions. So in thermodynamics, what you have to make out, one is graphical model of the questions, cycle, okay, they are the easiest questions. Or the next is they'll give you the process and temperature changes, you should be able to find Q and delta U and W and even molar specific heats for all the process. And sometimes they'll be giving you Q absorbed or rejected, like that they'll be giving you some questions. I've given you the table, so just go through that table once, okay, that is another model. And with partitions also they'll be giving you, right? So these are all the models we try to cover in a thermodynamics, okay, and previously in the heat transfer also. Hope you have understood this session properly, and from now onwards you will do the questions in thermodynamics and heat transfer more easily, okay, and scoring good marks in these particular chapters in the final exams. Okay, thank you very much.